Welcome to this Grade 8 Geometry Explainer. If you're looking to master similarity transformations and similarity criteria, well, you're in exactly the right place. Today, we're going to take some geometric concepts you already know and stretch them, literally, into a whole new dimension.
Here's our roadmap for today. First, we'll look at congruence versus similarity. Then we'll define dilation and similarity. After that, we're proving the AA criterion. We'll do a quick pause and check to make sure it's all making sense. And finally, we'll wrap up with a recap and a real-world transfer question. Okay, let's dive into this.
Section 1. Congruence versus similarity.
So think back to what you already know about moving shapes around on a coordinate plane. You know, sliding, flipping, and turning them. On one side, we have congruence. Congruence is all about rigid motions, rotations, reflections, and translations. These moves perfectly preserve both the exact size and the exact shape of the figure. It's like picking up a puzzle piece and just moving it somewhere else. But then, on the flip side, we have similarity. Similarity takes all those rigid motions and throws in a real game changer: dilations. With similarity, the shape stays exactly the same, but the size? That can completely change.
Before we get too deep into the new stuff, let's just firmly ground ourselves in the precise mathematical definition of congruence. Simply put, two plane or solid figures are congruent if one can be obtained from the other by a sequence of rigid motions. Basically, if you can rotate it, reflect it, or translate it to match another figure perfectly, boom, you've got congruence. It's simple, it's solid, and it's rigid.
All right, moving on to Section 2, defining dilation and similarity.
We're about to add a seriously powerful new tool to your geometry toolkit. Meet the dilation. Mathematically speaking, a dilation is a transformation that moves each point along a ray emanating from a fixed center, and it multiplies the distances from that center by a common scale factor. Now, if that sounds like a lot of math jargon, just think of a movie projector casting an image onto a big wall. The projector's lens, that's your fixed center, and how far back you pull that projector determines your scale factor. Those two crucial pieces of info, the center and the scale factor, are exactly what dictate how our shapes resize.
And that brings us to the actual definition of a similarity transformation. Are you ready? It is simply a rigid motion followed by a dilation. That is literally it. By combining what we already knew, moving shapes around without changing them, with what we just learned, resizing them with a scale factor, we get the exact definition of a similarity transformation.
So here's how it plays out. When a figure undergoes a similarity transformation, its side lengths change proportionally based on that scale factor we talked about. But, and this is absolutely vital, all the corresponding pairs of internal angles stay exactly the same. They remain congruent. So a triangle might get twice as massive, but its angles don't get any wider. This little characteristic right here, it's the golden key to really understanding similarity.
Let's head into Section 3, proving the AA criterion. Let's see how this builds into a really cool shortcut for triangles, known as the angle-angle or AA similarity criterion. It states that two triangles are similar if just two angles of one triangle are congruent to two angles of another. Now you might be wondering, why only two? Well, remember that the interior angles of a triangle will always, without fail, add up to a straight line of 180 degrees. It's a baked-in mathematical rule. Because of that, if you know two angles match, the third angle literally has no choice but to match as well. So finding just two matching angles actually gives us the whole shebang.
Let's walk through this explicit correspondence step by step so you can really visualize it. Step 1. You map angle A on your first triangle directly to the corresponding angle D on the second one. Step 2. You map angle B to the corresponding angle E. Because of that 180-degree rule we just talked about, step 3 is basically an automatic conclusion. Those third angles must also map perfectly onto each other. And because all corresponding angles are congruent, you have completely justified that these two triangles are similar.
Moving right along to Section 4, pause and check.
Now, to make sure this is all really sticking, I'm going to invite you to pause this explainer and test your understanding. Here's your first scenario. If a geometric figure undergoes a sequence of only rotations and reflections, is the resulting figure similar to the original? Go ahead, hit pause right now. Think about our definitions of rigid motions and similarity and lock in your answer.
Okay, ready? The answer is yes. If you got that, awesome job. Rotations and reflections are rigid motions, meaning they create perfectly congruent figures. And remember, preserving both size and shape perfectly satisfies the requirements for similarity. Congruence is essentially just a special VIP case of similarity where your scale factor happens to be exactly 1. It totally fits the similarity rulebook.
All right, let's try one more. Pause and check 2. Let's say triangle 1 has interior angles of 40 degrees and 60 degrees. Triangle 2 has interior angles of 60 degrees and 80 degrees. Based on that angle-angle criterion we just covered, are these two triangles similar? Go ahead and pause again, do a quick mental calculation using that 180-degree rule, and I'll be right here when you're ready.
So what's really interesting about this one is that you can't just trust a quick glance. At first look, the listed angles don't seem to match up to the AA criterion, right? But if we actually do the math for triangle 1, we take 180 degrees minus the sum of 40 and 60, which leaves us with a third angle of 80 degrees. Now look at triangle 2. Its given angles are 60 and 80, so both triangles share a 60-degree angle and an 80-degree angle. Calculating that missing angle reveals their true similarity. The AA criterion is beautifully met.
Finally, we arrive at section 5, recap and transfer.
You guys have done an excellent job following the logic today. Here is a quick explainer recap to lock in the core concepts we've explored. Just look at how nicely each idea stacked on the last one. We started with rigid motions, rotations, reflections, translations, which preserve size and shape. Then we introduced dilations, which resize figures using a specific center and a scale factor. Next, we combine those ideas, defining similarity transformations as rigid motions plus dilations. And finally, the AA criterion showed us how to prove triangle similarity using just 2 corresponding angles, because that third one is mathematically locked in.
Now, to wrap things up, I want to leave you with a real-world transfer question. Imagine an architect hands you a blueprint of a massive building. This blueprint was created using a geometric dilation with a scale factor of 0.05. How do the angles of the walls drawn on that blueprint compare to the angles of the actual physical building once it's constructed? Well, the answer relies on everything we've talked about today. Remember that while a scale factor drastically changes the lengths of the corresponding sides, shrinking a skyscraper down so it fits on a piece of paper, similarity transformations perfectly, flawlessly preserve those corresponding angles. A 90-degree corner on the blueprint is a 90-degree corner in real life. But it really makes you think, right? If similarity perfectly preserves angles, regardless of scale, how do engineers account for the physical weight and stress that definitely does change when a building gets 100 times larger? That right there is where geometry meets physics. Thank you so much for joining me in this explainer today, Focus Learners. Keep exploring, keep questioning, and I encourage your continued curiosity in the amazing world of geometry.